Okay. I hope you had a nice lunch break, and welcome you back from lunch. And our last speaker of the day is Laure Dumaz, and she will tell us about some more about the one-dimensional Anderson Hamiltonian with white noise potential. Please.
Yeah, so thank you. So I try to speak loud because unfortunately I have a dress and so I cannot use this. And so,
boy, is he going to get in trouble with the authorities?
So thank you for the invitation. It's a great workshop. I'm very happy to participate. So it's joint works with Cyril Labbé, and it's a second part of our work. But so let me just recall what we are talking about here. So we are talking about a one-dimensional Schrödinger operator, which works as a differential operator. And it's very simple. There is a minus a Laplacian plus multiplication by some function v that we call the potential. And it's a nice interpolation between the Laplacian and the multiplication by the potential v. So those two operators have very different spectral properties, and so you can wonder when you add the two, it makes an interpolation, who wins. And the talk, again, we focus on a very special choice, which is the white noise. And so you can construct, as Cyril said, a proper self-adjoint operator, which is well-defined in some subdomain of L2. And there is a parameter L here, because I will only talk about the operator that acts on a finite segment here of size L. And so this L is important, an important parameter, and so I keep it in the notation of our operator. And we put some Dirichlet boundary conditions, but that we could choose also Robin boundary conditions. And just to advertise a bit, so what are the advantages of the white noise? Why such a choice? First, it's natural because it appears in many scaling limits. And also for us, it's very convenient that it's so explicit and that we use all its nice properties to derive fine results. So our goal was really to study a specific operator, but then to say a lot of things about this operator. But the inconvenient, the major inconvenience, but it's the only one, is that it's irregular, and so we have to deal with this irregularity in our proofs. And we would like to study the spectrum of this operator, and we take the same approach as Cyril has said, and so and it's also the same approach that usually is used also for random matrices. Namely, we fix some energy E, and then we zoom around this energy E, and so we look at the eigenvalues, and we will just look at a finite number of eigenvalues near this energy E. And when L goes to infinity, well, you have a lot of points here, and so you have to zoom at a proper scale, so that when you look at this as a point process, a random point process, you have something non-trivial at the lead, still a point process, random point process. And so when so you fix your favorite energy E, and you do that, and then you can wonder for each of those eigenvalues, you can look at the associated eigenvector and what its shape. So it's a random. All those things are of course random because the white noise is random, and so you can wonder what it looks like this eigenvector. Okay, is the setting clear? And so Cyril presented this morning 5 regimes. So I just recall 2. When the energy where you look at is much smaller than the length of the box, then the eigenvalues are Poisson and the eigenfunctions are localized, as is usually expected that the two go together. And we even know the localization length. And there is a critical regime, but there was also a top one. But the critical regime is interesting because the eigenvalues now have a repulsion, and the eigenfunction associated to those eigenvalues, they are delocalized. So when you look at their A2 mass, you put some A2 mass everywhere on the segment. And so I will focus now on this particular choice. And I will recall just what Cyril has presented. So if you zoom, you look at the eigenfunctions, and as Cyril mentioned, they oscillate a lot, like crazy. So they do a lot of oscillation like this. So a good way to look at this eigenfunction is just to look at its induced probability measure in this way. So your segment of size L becomes a segment of size 1, and you look at this object as a random probability measure. It's a probability measure because here we take eigenfunctions that are normalized in L2. And so now you have something more convenient object, and you can wonder what's happening when L goes to infinity. And so you can look at the point process, where on the first coordinate here, you look at the eigenvalues really near the energy E, and the second coordinate, you look at this random probability measure. And the result is that it converges towards a random point process, which is characterized by coupled diffusions. And about the first coordinate, so about the eigenvalues, as Cyril mentioned, it's distributed as the SCH2 point process, which was introduced by Krzyzewski, Balko, and Virag in 2012. And it was in the same context, was a context of discrete random Schrödinger operators. And what is nice is that in their papers, they compute things about this point process. It's characterized through diffusion. So, but for example, they can show that there is some repulsion between the points, and this repulsion is in fact much stronger than, for example, for those of you who know the random matrix models, it's much stronger than the sine beta repulsion. So it's not sine beta. SCH2. And about the second coordinate here, so it's distributed as exponential of Brownian motion plus a two-sided Brownian motion plus a drift around the uniform point here. So okay, so we have something non-trivial. And yes, and Cyril mentioned that, so maybe I just pass this through. And Cyril also mentioned that, in fact, in the localized regime, we already have this shape when the energy is much larger than 1. And one aspect that Cyril did not describe is that you have here a random point process at the limit that is non-trivial. You also have eigenvectors, which are also non-trivial, and so you can wonder if we can obtain a convergence at the level above. So as Benedek Valco yesterday told us, when you have several levels where you can obtain the convergence, and the best one somehow would be to have the operator convergence. So the full object converges towards a non-trivial. So is it the case if you zoom it correctly, you rescale correctly, sorry, HL around the so that what you keep at the limit is really the large energies. Does it converge to a non-trivial random operator? So that was the question. And so here is the answer. So yes, it converges, but we have to perform some non-trivial transformation to have the convergence, and I will explain just after. But what I would like you to look at is the limiting the limiting operator that we obtain, because we were quite happy to obtain such a nice form. So you see it writes in this way. So you have a first part, which is somehow 2i's times the first derivative, So it's this operator now is just you differentiate only once. But the difference here is that I should have stated first is that what is the Hilbert space where this operator acts? It's the usual L2 starting from a segment of size 1, but it's R2 valued. So it's like if you when you have a function f, you think of a couple of function f1, f2. So you SCH2, like you have a function f1, f2, and so you see the action. And so there is this first part, which looks like a Laplacian. And then the second part looks like the multiplication by a potential. But now the potential is a 2 by 2 matrix, symmetric, and what is inside this 2 by 2 matrix? There is this current of torques. It's a parameter, and it's simply it's just E over L. So it's just a parameter that appears naturally when you take this limit. And then there are two dB, dW1 and dW2. These are three independent white noises. So you started with one and you have three. So that's nice. And what can I say? And yet, and you put some Dirichlet boundary condition for the domain of this operator. So a few comments. So about this convergence. So we proved that this convergence holds in low, in the strong resolvent sense. But we also proved that there is convergence in low of the eigenvalues and eigenvectors. So we do not miss any information about the spectrum in this limiting operator. And what is nice about this operator is that it was already appearing in the work of Edelman and Sutton as a conjecture for the bulk of limiting random matrices. So it's nice to see that it appears here indeed that we have such a form. Other remarks. So as I mentioned, the limiting operator, it acts on R2 valued functions. So it means that, but we started with just R valued functions. So it means that in fact we have to enlarge the initial space, okay? And so the transformation of HL that we have to perform is non-trivial. We have to add a second coordinate. And another issue is that in fact this operator is not properly defined in this form because there is multiplication by white noise. And we have seen this morning that it was a problem even for the Schrödinger operator. And so an elegant way to define it is to use the beautiful theory of Valco and Virag, the Dirac operators, and so we define it this way, and then we transform it into this operator. And I will in fact, I did not say what was the plan of the talk. So the first part is about those results, and then there is a second part, which is a lot more about those Dirac operators. And our approach is quite robust, so it can be applied, in fact, to other models. So, for example, the bulk of tridiagonal matrices or other differential operators. So, how does it work? We rescale first the operator around the energy E. Okay? So it means that the first thing you do, you take HL, you subscribe E, and then you rescale, and you rescale also the function so that they act on L2 of -1/2 instead of something of size L. That's standard. But then you would like to have an operator limit. So you would like that the eigenfunctions converge, but of course, I told you they are oscillating very much. And so they oscillate too much to have a limit as functions. They have limit as probability measures, but not as functions. So we need to find a way to remove those oscillations. And to do that, we consider both the eigenfunction and its derivative. So that's how we enlarge the initial space. So that's why there is this R2 valued functions. And then, from that, we rotate so that we remove those oscillations. And so first, we embed our operator, which was initially acting on the L2 R-valued functions, into an operator which acts, in fact, on a Hilbert space, which is of this form. It's a L2R Hilbert space. So you see it's defined for R2 valued functions. And here, R is just positive, not positive definite. It's a symmetric 2 by 2 matrix. And so this character product means has to be finite. And so, of course, you have a whole equivalent class, and so you have to remove that. And so let me just describe, because it's simple to see what's happening at the level of SDEs. So let me describe what's happening. So SDEs, I mean, when you will look at the eigenvalue problem, and you will have naturally SDEs for that. So here is a rotation matrix. And you take E prime, which is of order E at the power 3/2. And you note that if you take some function defined this way, you can remove easily the oscillation by just multiplying by the rotation matrix, of course. And now you do that to the solution of your differential equation, which is this one, defined this way. Okay, so HL phi lambda is equal to lambda phi lambda. So first, you consider it as a system with phi lambda and its derivative. So a system with two coordinates. You rescale things, etc., so that you look at the correct lambda is of order E here, and okay, and you rescale. I said the space is of order L, and so you put it on something. So you do the rescaling, then you unrotate, and then you obtain something. And this something is the solution of this SDE. And I wrote it this way, of course, so that it makes transparent the link with the limiting operator. So here is the new thing we keep track of, and it's a solution of this SDE. Okay. And what is interesting is that you have a 2x2 matrix here appearing, which depends on the Brownian motion here is the integrated white noise, and so you have those three. So you have those three Brownian motion appearing that are of course correlated here, and they become uncorrelated in the large L limit. And so here is the solution, and here I just wanted to show you the similarity with the limiting eigenvalue equation. Okay. So at least at the level of SDs, it's this operator appears naturally. Now I would like to make a link with the operators of Valco and Dirac, but maybe so I stop. Okay, so it's you can follow this second part of the talk without even if you don't care about this special operator or this white noise. So it's a beautiful link with hyperbolic geometry. And so for hyperbolic geometry, like it will be convenient for us, it will be the good space to consider it, the hyperbolic geometry on the upper half plane. Okay, and so what is it? So you have, when you look at 2 points here, so you could say what is the Euclidean distance between the two, and you have also the hyperbolic distance. And this hyperbolic distance, like it explodes. You don't like to be close to the real axis, so it explodes when you are near the boundary here. So you have the special point I, for example, and it's at an infinite distance of the point 0 here on the real axis. Okay? And so it explodes, and so it means that if you want to find the shortest path from this point to this point, what you have to do is something like this. Okay, the geodesics are these those circles here, so half circles, and also the lines, so vertical lines. And so it's like as your distance explodes when you are near the boundary, it's like of course you prefer to first like go up because the distance is smaller, and then and it's a very nice geometry, especially because you have this the fact that like parallel lines they touch at the boundary points. Okay, so that's hyperbolic geometry, and of course, if you like, you have a formula to describe what is the distance really between point Z1 and Z2. And you have also another. You can map everything to the unit circle. We won't use it a lot, but the same story works also for the unit circle. And first question you can ask about this when you have a hyperbolic geometry is what are the isometries, and isometries, I guess. And for H, the situation is very simple. They are given by the Mobius. So I only look at isometries preserving orientation. And they are given by the Mobius transformation. Which writes this way. So you have A, B, C, D, which are all real. Okay, for usual Mobius transformations, you can take complex parameters, of course. But here, what is nice is when all those parameters are real, then it adds from H to H. It's a simple computation. And the other thing, you need that AG minus BC is completely positive. So all the isometries preserving orientation are given by those Mobius transformations. And there is a nice way to write that as a matrix. And it's a group, and so if you want to conjugate two Mobius transformations, then it corresponds to do the same, the product of the matrices, etc. So everything works well. And now what you, another thing you can do is to classify those isometries, and you have three types. I really don't know how to use it. Is it? I don't know what's it. Three types. You have three types, and you classify them according to their number of fixed points. And so it's easy. What you have to according to the number of fixed points. And so what you have to solve is it's very basic. And so you have either delta. Okay, either delta is positive, and then you have two real solutions. So in your upper half plane, so when you look at the fixed point, it means that I should have mentioned that, in fact, you can extend, of course, the action of this Mobius transformation to also H bar, which is H with its boundary. And the boundary is just a real line and the point plus infinity. Okay. And so it means that you have two solutions here, so that's a fixed point. Okay, and let's look at the particular case where one of these when one of those fixed points is 0, and the other one is plus infinity. Then, in fact, you can see that your isometry is doing something like this. It's a dilatation. Okay, so it means that it acts like this. It's simply a dilatation when those two fixed points are 0 and infinity. And when they are not 0 and infinity, but other points, well, you have lines like this corresponding to the fixed line of your transformation. Okay? So that's this case, and so I call this case dilatation because I see that as a dilatation, but I think it's not standard in this dilatation. Okay, and that's this case. The two fixed points are like this. That's a less interesting case. Okay, when data is equal to 0, so it means that you have only one fixed point. Here. Suppose that your fixed point is plus infinity. Then what you would have here is a translation. Okay, so it's simply a translation. And so when your fixed point is in the real line, those lines here, so you can really, I hope it's clear, but you can really map. Here you have always Mobius transformation sending, for example, this point to this point and this point to infinity. Okay. So you can pass from one to another. Here it's the same. You can pass thanks to Mobius transformation from this fixed point. You can put it at infinity. And then you have those lines, and those lines, when you look at them in this model, make circles like this. Okay, so that's translations. And the last case. The last case is when you have when delta is negative, and so you have two solutions, and one is the complex conjugate of the other, and so you have only one solution in H that is somewhere. And here, a good way to see that is to map it to map this to the unit disk and to put this point, which is your fixed point, to 0, and then you have rotation. In this model. Okay, and the rotation, it also makes circles. So that's the three cases. And now you can wonder what's the link with this topic. Okay. Like first, maybe we have seen during Elliot talks something very similar. So an application of that. And okay, that's rotation. That is very nice. Is that if you take a Jacobi matrix, where the BI's are positive and AI's are real numbers, then when you solve the kind of eigenvalue equation, G u equals lambda u, and then you look at the transfer matrix, then the cool thing is that here you have only real numbers. And so in your transfer matrix, in fact, it will be Mobius transformation that preserves the upper half plane, just because here the numbers that appears here are real, just for this reason. And so it means that the transfer matrix here, if I'm not to do the computation, but if you look at this, the transfer matrix would be this one, minus bk minus 1, k 1 0. The transfer matrix acts on u k uk minus 1, k can say that has a Mobius, has an isometry of the upper half plane. And then the next question is, but what's the type of this isometry? But it means that you can study really the eigenvalue equations as a composition of small isometries in this sense. And in fact, yesterday, it was yesterday, Elliot had 3 types of regimes here, and those 3 types really correspond to that. So I think the first type was like hyperbolic, so we call this hyperbolic. This is parabolic, and this is elliptic. Okay, that's the 3 types that appears here. It makes a nice name. And now the question is, can we define natural operators, self-adjoint operator? I still want to be in the self-adjoint case. Operators such that the eigen, so let's say tau, such that the eigenvalue equation expressed nicely in terms of those in this hyperbolic setting. Okay, so that you can see that as such that this evolves as nicely, let's say, in the hyperbolic. Half plane. Okay, and so it's very vague, but nicely, let's say that, for example, you have to, you stick to one of those cases, so let's say translation, and then you only perform translations, okay, you do not mix the 2. Or you do only rotation, so you stay, so for example, for translation, and we'll see dilatation is not very interesting, translations or rotations. And let me do the translation part, because usually it's not treated, and also because it's there is a very nice link with Schrödinger operators. So in fact, we'll see that Schrödinger operators can be really seen as operators that act really nicely, that makes translation, in fact, so that the evolution of the eigenvalue solution really evolves as making translation in the hyperbolic half plane. Okay, so let's do that. So the translation case. So let's do first the simple exercise where your point is really fixed here and is plus infinity. So that your evolution is really basic. And so let's define the solution of this equation. And here, in fact, I choose this because it's an infinitesimal, it's a derivative of it's an infinitesimal step of for a rotation with respect to plus infinity. Okay, so this is just a translation with respect to plus infinity, and so that's infinitesimal step. Okay, and so you can see it's very simple computation that solution, and you look at its projection. Here, it simply follows this equation. T plus. Okay, so that's simple. Next, you can say, okay, but that's very boring because our fixed point is plus infinity. Let's see what's happening for other fixed point, but okay, it would be also very simple. But then now a nice interesting case is when now the fixed point is no longer fixed anymore for the whole time, but varies with time. And when your fixed point varies with time, so let's call this path gamma of t. So now you have your fixed point is in the boundary, right? And so you have some t gamma of t, which is your fixed point that belongs to the boundary of H. And you want to perform an infinitesimal translation with respect to this fixed point. And so it's easy to derive what should happen. So first you take your function, and then you want to put this fixed point to plus infinity, thanks to Mobius math, so that you know what you have to do in the next step. So let's do that. So here we put a Mobius, which sends gamma for time t, okay, which sends gamma of t to plus infinity. But it's easy to figure out what is the correct, one of the correct one. You have many, of course, but the choice does not matter. And so this does the job. Then you do your translation with respect to plus infinity, infinitesimal translation, and then of course you have to go back and to put again the point plus infinity to gamma of t. Okay, so the inverse of this Mobius transformation, and so it's gamma of t minus 1, 1, 0, and then there's lambda, and here it is. Okay, so it's a multiplication of 2 by 2 matrix, so it's simple, and in the end you get this type of things. And I said here, I can also add an additional parameter, which is, I can also say, okay, here the speed is always the same, but I can also vary it, right? And so, okay, other case, I can, more general case, let's say, more general case. I can look at the same thing, except I add a speed that can vary with time. So I know some sigma of t, which is a speed. So instead of being always lambda, you can vary with time the speed, and then you have this. So recall that this is just the fixed point of the fixed point of the isometry. This gamma of t belongs to R plus infinity. Okay, so you do that, and it turns out that in fact the Schrödinger operators, they all write in this form. Sigma of t is speed, additional speed. They all write in this form. Okay? So in fact, so yes, maybe first fact, this is a self-adjoint operator because you can write it. Another way to write it is this way. This is a self-adjoint operator, so you can another way. I mean, this is the eigenvalue equation. Sorry, of an operator. So it writes this way. And then 1 minus gamma t minus gamma t gamma t. Okay, so I hope the choice was good. This is a sigma, and this is a gamma. Sure. And so it is the eigenvalue equations of some self-adjoint operator, and this self-adjoint operator acts on this space, this L2R space, where R is this symmetric matrix. It's a symmetric positive definite matrix. Oh no, not definite. It's a symmetric. Its determinant is equal to 0, but it's still a positive and symmetric. Okay, so of course you have to remove up to the equivalent, the usual equivalent class. So this is the eigenvalue equation of the self-adjoint operator. And in fact, you can really map all the Schrödinger operators to operators of this form. How you do that? So what I think that's very nice. Schrödinger operators are of this form. And so Schrödinger operators, so we have seen 1D. So it writes like this, the eigenvalue equation. And how can you map this to this? Well, first, maybe let's rewrite a bit things. So we look at f prime, and then we see what the equation it solves. Okay, and then there is this nice matrix that appears here, V minus lambda. So I just rewrite the Schrödinger equation into a form I prefer. And then I can define the transfer matrix for the eigenvalue equation for lambda equals 0. And I call that T0. So T0, it's a Neumann and the Dirichlet solutions for lambda equals 0. Okay, so it means that its evolution is simply given by its derivative is 0, 1, v, which is 0 here, like this. And then if you express your solution here, but in the coordinates of the Neumann and the Dirichlet solutions, then there will be solution of some equation of this form here. Okay, so if we define V, which is equal to T0 minus 1 F prime here, and I look at the eigenvalue, I look at the differential equation for V, the simple computation, and you can see that in fact V solves this equation with this matrix UN, EG, UN, G, EG, F. Okay, so that's very nice. And also, so it means that, in fact, your eigen, like in those coordinates, what is your eigenvector doing, or at least any solution, in fact, of the eigenvalue equation, what it is doing, that it's simply performing a translation with respect to the point minus so there's this translation with respect to UG over UN at speed lambda UN square. Okay, so it's a nice link. And now what's happening for rotations? So now the question is the same, but except that you want that to look at rotations. So let's do the case for rotations. And so same story, I will start with rotation with respect to I, and that I is fixed the whole time, and I perform the rotation with respect to that. Turns out that, in fact, the rotation with respect to I, it writes very simply. It writes like cos theta minus sin theta, cos theta is a rotation of angle theta. Yes. Okay, I'm not sure about so this is a rotation of angle theta around I, and then if I look at the eigen at this the solution of this you can see easily that it performs a rotation around I. Okay, so that's simple. And now same story. So you want an operator for rotation. Hyperbolic, of course. Rotation is always hyperbolic here. Hyperbolic rotation with moving center and also maybe moving speed. Okay, moving center gamma of t. So now you have some function gamma of t which belongs to h, because I am in the rotation case, so it's really inside the upper half plane, and I want to find an operator for that. And so I can do the same. I start with my function, and then I put the center to I, where I know what I can do. So I put the center to I here, and this is x. So x is this one. It puts, okay, let's define. So the center is gamma of t, and its real part you can call it x of t, and its imaginary part, which is strictly positive, you can call it gamma of t. And so you have this x, so you take your function, then you take the Mobius transformation, which sends gamma of t over I. Then you do this infinitesimal rotation, minus 1, 1, 0, and then you put back gamma of t where it should be. And so you do that, and in fact, you can see easily that it's equivalent to this form. Gf is equal to just a short computation gives you this graph. Okay, so this evolution here, which is really like the evolution of an infinitesimal rotation with respect to a center gamma of t that evolves with time, follows this simple equation. But here we are it's even a nicer case than before, because here we have some matrix that I can call R, as in the previous case, but now it's definite positive. Okay, so the L2R space here is really of dimension 2. Okay, and so I can really even invert this, put it on the other side, and so that I have a proper differential operator here directly. write this way. Gamma J F prime equals lambda. Okay. And so this is an operator. This is an operator. Oh, the whole thing. And it acts on L2 of R. These those functions, so you have to do that during a finite or infinite time, and then the space is this one. Okay. And so what's the result, the main result here? Because there is no result, it's just correspondence for the moment. First thing, that is the same way, in fact, the operator which has of this form, so operators which write in the same way as the one we obtained with Cyril, so like this, plus a multiplication by 2 by 2, now V is a 2 by 2 matrix, symmetric matrix, symmetric matrix. The same way you can perform a computation and show that those operators are equivalent to those ones. If you unitarily change them, you can it acts here on this space. 0 t. So this is just okay. One. So it acts on this Hilbert space, and here this is really an operator that can be mapped to this one. So the same way as the Schrödinger operators are linked to the translation operators. And can be unitarily. So I just write what I said. Unitarily transform to an operator of this form. To an operator 2r minus 1 j for some of course well chosen r. And the main result of this is given by Valco and Virag. Who have proved in the sine beta operator that indeed you have an operator which performs only rotation, so it's really an operator looking like this, which correspond with spectrum correspond to the sine beta point process. So there exists the sine beta point process is the eigenvalue of an operator to beta, which really writes as an hyperbolic notation with r of t. And what is nice is that here in this case, r of t expressed very well. There's a known object. It's just a hyperbolic Brownian motion that is time change. Hyperbolic Brownian motion, time change. So what is really nice is that here it is very natural, a natural object here. And of variance and so to conclude, exactly, so the operator I've shown you here that appears also at the limit of the one-dimensional white noise Schrödinger operators really is an operator of this form, but that can be transformed into an operator of this form here. And here is the same thing, except the hyperbolic, we also have an hyperbolic Brownian motion here, but it's not time change. So it's also very natural the operator that we have in the limit in this hyperbolic description. And just, maybe just one word about why is it useful. It's useful because then you have a geometric picture. And so usually when you have an operator, I did not say, but here I just describe the evolution of the operator, but the domain is very important. And you have usually boundary conditions, etc. And so here, what you can do is really you look at the eigenvalue, you look at, let's say, in the rotation case. So you have some lambda, you would like to look at the eigenvalue evolution. Your domain of your operator, you put it has a left boundary condition, so you start from this left boundary condition. Then you follow the hyperbolic rotation all the time you need around this gamma of t here. So every time you move, etc. You can make many terms. You can go to plus infinity and then come back, etc. And the question is, do you, for this lambda, so you look at this evolution, and the question is that, is your terminal point, at least in the limit circle case, so you see here it's your left boundary condition. And the question in the limit circle case is, at time t, is your evolution, so your evolution, which is really characterized by this rotation and described by this rotation, does it end at the point u1 here or not? If it ends at u1, you win, you have an eigenvalue. If it does not end at u1, then you can maybe count the number of times it passes through u1, and then you have, thanks to Sturm-Liouville theory, some information about the spectrum that is there. Thank you for your attention.
Thank you very much. Questions, comments? Yes, Sasha.
I have a short question which belongs to earlier parts of your talk. What can you say about model industry?
About
The product of R and an interval of one. You consider the model and
on the strip
yes.
instead of a line.
Yeah, I presume regularization is much more difficult than the 1D case, so it's probably doable. But then the question is, to prove localization, you would have to avoid the Gaussian Mergulis theory somehow. Is there a chance that morally localization should fall, but it should be within the realm of the technology, but
Yeah, I agree. But so morally,
but it's not so easy because it's not.
yeah, it's an interest. I'm interested to look for this. Indeed, it's the next most available case. Let's say so. It would be nice and even to. There, you have done also some work about the street. You have about this case where they found some statistic of GOE in the case of the strip, but when the strip becomes a line, so when it's very thin, so
One is not
yeah.
binary, it's not your transfer matrices are not factors dimension anymore in this people discipline. I mean, I'm sure you can do coupled
Yes.
couple ten of these. This is okay, but if you're to proper
Yeah,
continuum
yeah.
strip is
Exactly.
Yeah.
And so I guess you could consider this CS operator on the infinite line.
Yeah, that's
Did you
true.
say anything about that?
Yeah.
Two copies of R? Or two
It's-
copies of R, as opposed to just two copies of R? Or vector value functions in R?
Yes. So, and in fact, those kind of operators should be the limit of the crossover regime. So, the word R, so it's localized. It has localized eigenvectors, and and can also its root can be also defined and everything. So I think it's an interesting operator.
Yeah.
So in cases like what you started with, where you have a Schrodinger type operator converging to the Dirac type operator, does the geometric picture describe how this transition occurs?
Yeah. So what is really strange here is that you see you have something that starts to be with a fixed point which is on the boundary, and suddenly it jumps to the upper half plane, and that's very strange. So just because in the end there
Does it maybe rule out a type of convergence? That there's some type of convergence which is not possible because it's jumping up or something like that?
Yeah, it's more about you first. So in the matrix, okay, I do not have my slides anymore, but there were three. So if you really write it on a Dirac form, the operator that we deal with, and so there is this 2x2 matrix, and there were three noises, but they were highly correlative, and in fact there were so. But then in the end they decorrelate, and it explains a bit, I think, but it's only in the end. And for any finite n, they are very close to each other.
More questions, comments?
If not, let's thank Laure again. Thank you.